Okay, so we will do one more limiting reactant problem just to get it under our wings. So let's do question number 6.43 from your book, page number 239. The question reads as, the balanced equation for the reaction of nitrogen and fluorine to form nitrogen trifluoride is given. N2 plus 3F2 gives 2NF3. Assume that 10 grams of nitrogen is mixed with 10 grams of fluorine. Then we have to answer the two questions. First part, what is the limiting reactant? And then what is the amount of NF3 in grams that can be produced? Okay, let me just write down the amounts and then I'll give you the book back, Heather. So we have N2 and F2, that is 3F2, forming 2 NF3, and what we are given is both 10 grams. Okay, so we have the balanced equation, both reactants given in mass. So what is the first step? Converting the mass to moles. So let us convert both nitrogen and fluorine to number of moles. So 10 gram of nitrogen multiplied by 1 mole per, what molar mass I should use? Yes, this whatever is given. So remember here N2 is acting as your reactant, right? So you want the molar mass of the N2. So what would be the molar mass of N2? 28.02 grams. So grams and grams goes away and you will get the number of moles. Now similarly calculate how many moles of F2 you have. So again 10 grams of F2 multiplied by 1 mole per molar mass of F2. How much? 30? 30? 38. So this is the first step, converting the mass of both reactants to moles of both reactants. So how many moles of each you have? Nitrogen we have how many? 0.356, and fluorine 0.263. Okay, so instead of the grams now we have both reactants in number of moles. Once we get the number of moles, what do? Pick up the first, whatever is given, pick up the first one's number of moles and calculate theoretically how many moles of the other reactant you need using the mole ratio. So for nitrogen you have 0.356 moles. How many moles of fluorine you need for a complete reaction? How do you calculate that? Multiply this by mole ratio between fluorine and nitrogen. Which one goes on the top, which one goes on the bottom? Fluorine, because that's what you are looking for. How many moles of fluorine you need? So that number goes on the top. So 3 moles of fluorine per 1 mole of N2. Oh, this is moles of N2. So how many moles of fluorine you need for this reaction? 1.068. Oh. Okay, so what you just calculated here, this is the theoretical value. Okay, this is the amount of fluorine you need to react with 0.356 moles of nitrogen. Now you compare this number with the number actually you have. You have 0.263 moles of fluorine. What you need is 1.068 moles of fluorine. So, what is the limiting reactant? What is your logic now? This, when you look at these two numbers, it won't just tell you anything. You have to think that through your head. You need this much fluorine, but you have only this much given, right? So what you are given is less than what you need. That means this is the smaller amount present, so this will be your limiting reactant. In case this number was smaller than this number, then you would be thinking, okay, I am given more than what I need. Therefore, that is the excess reactant, fluorine. So, nitrogen should be the limiting reactant. That is how you use your logic. There is no clear-cut formula or shortcut to do that. You have to do this calculation and compare the two numbers. So, this is the smaller amount, or the amount you need is more than what you are given. Therefore, this becomes the limiting reactant. So, fluorine is your limiting reactant. Is this part clear to everyone? So far what we have done. So once again, convert both mass to moles, then pick up the first reactant's number of moles, calculate how much you need of the other reactant using the mole ratio, then compare the numbers, what you calculated, what you are given in the problem. Then compare which one is smaller. If what you are given in the problem is more than what you need, then yeah, the word more than, that means that is in excess. So the other one has to be the limiting reactant. What you are given in the problem is less than what you calculated, then yeah, less than means that is present in the smaller amount. So that should be the limiting reactant. So this is the first step, you identify the limiting reactant. Now the second question is how much NF3 can form in grams. So what you need to remember, the amount of limiting reactant will determine the amount of product that can form. Remember the cheese sandwich example. Okay, you had 5 slices of cheese, so only 5 sandwiches could be formed, right? So whichever is the limiting reactant, that determines how much product can form. So this is your limiting reactant, fluorine. So this amount will determine how much NF3 can form. So start with that number of moles of the limiting reactant, which is 0.263 moles of fluorine, that is your limiting reactant, and calculate the number of moles of product that can form. So how do we calculate that? Multiply by mole ratio between the product and the limiting reactant. So now you are looking for the moles of product. So that mole ratio will go on the top. 2 moles of NF3 plus 3 moles of fluorine. That's what the mole ratio between NF3 and fluorine is, right? Comes from the balanced equation. So moles of fluorine goes away, and calculate what is the number of moles of NF3 that will form. How much, Cassidy? 0.175 moles of NF3. Is the question asking how many moles of NF3 will form? No, that is asking how many grams of NF3 will form. So what is the last step? Convert this moles to grams using molar mass of NF3. So multiply this by molar mass of NF3. What is the molar mass of NF3? One 28 plus 38. What did you say? No. N is 14 something. 14.01. Okay. And 3 fluorines. 71.01 grams. Okay. So moles and moles will go away and you will have your answer in grams. How many grams? .42 grams. 427, so 12.43 grams. So that is the amount of NF3 that will form in grams. Yes. Say that loudly.
Did you say last time that we were in class that only half the lecture got recorded?
Half of, well, the video is all recorded, but the sound is only half. I think what happened is when I fell down or when I went to the restroom, I accidentally hit the microphone and it got turned off. I didn't notice that until I finished the lecture. So the video is all full. All the PowerPoint slides, whatever problems you did, everything is there. But my voice is not there from half of the class. So it happens, this is just an additional thing you get. Every class you don't get the, lecture all the time. So this is one time you have to go back and, read from the book if you need more. But of course, as I said, the entire PowerPoint, all the problems we did, everything is there. Okay? So guys, again, one of these problems will be in your exam. Okay, exactly like this. I will give you the balanced equation. I will give you the mass of both reactants, and I will ask you to calculate identify the limiting reactant, and then calculate what is the mass of the product that will form. Okay, so it's two-step process. Please practice on this more. Questions so far? Okay, that's one slide. Okay, so we are going to start the next topic, which is percent yield. So the amount of product, which so far the calculations we were doing, like limiting reactant. One second, guys, I need to go and try clearing my nose again. What? If I don't come in 10 minutes, come and check. Okay, so the calculations we did so far, and let me check. Okay, that's on. Um, the amount of product that will form, what we calculated, those are called theoretical yield because you calculated how much product that can form, right? So that's called the theoretical yield. But what if you do the same experiment in lab? Like you started with, just like the previous example, you started with 10 grams of nitrogen, 10 grams of fluorine, you conducted the reaction, and you took the mass of the product that you obtained in the lab. Most of the time you will see that what you obtain in the lab is actually less than what you predicted by calculations, because those calculations assume that there is 100% reaction or all of the limiting reactant will react. That's what you are assuming when you do the calculations. But actually it doesn't happen. All of the limiting reactant may not react. Some molecules are left out. Some of them, we are not going into the details why all of them would not react, but you will see that if you do the actual experiment in lab, you do not get 12.47 whatever grams you just calculated. You might usually get an amount which is slightly lesser than that. And the amount you actually obtain in lab is called actual yield. Okay? So there are two things. One is what you experimentally obtained in the lab, that is called the actual yield or experimental yield. I think you have seen that word in the lab, right? In one of the lab you had a percent yield calculation, experimental yield over theoretical yield. So those are the two things. So experimental yield or actual yield is what you get in the lab by doing the experiment. Theoretical yield is what you calculate using the limiting reactant calculations. And percent yield is a ratio of these two, or percent yield is actual yield over theoretical yield multiplied by 100. Now when you write the yields, you can use either gram units or mole units or number of molecule units because it's a ratio. So this is how you calculate the percent yield. As I said, a simple equation, actual yield over theoretical yield. So remember, actual yield goes on the top. This is one of the common mistakes people make. So percent yield, this you can write that as A over T multiplied by 100, actual yield over theoretical yield multiplied by 100%. And sometimes people would kind of reverse it, that is they put the theoretical yield on the top and actual on the bottom. Please do not make that mistake. How I try to remember this is, if you remember this format, that is actual over theoretical, look at the alphabets. A and T. A is of course before T, right? So remember A first, then T in the bottom, not the other way. So this is how you calculate the percent yield. So let's see an example. Here is the formation of sodium chloride. Both are given in moles. So remember, percent yield can be expressed either using gram units or mole units. So you don't have to do any conversion from mole to gram. As long as both are in the same unit, you are good. You can use that. So if you have 0.2 moles of chlorine reacts with excess sodium, what does that word mean? What does that tells you? Sodium is the excess reactant and chlorine is the limiting reactant. Okay, and 0.4 moles of NaCl are produced. What is the percent yield of the reaction? So this is the amount of sodium chloride you made in the lab. Okay, so what is this number represent? Actual or theoretical? This represents the actual yield. So you have to calculate the theoretical yield, because for percent yield you need both numbers, correct? So how do we calculate the theoretical yield? We already know that chlorine is the limiting reactant, and you know what is the amount of chlorine you have. So theoretical yield is, how do we calculate it? Just like the previous problem, how do you, once you know the limiting reactant, how do you calculate how much product that can form? Looking at the mole ratio. So you have 0.20 moles of chlorine, and what is the mole ratio between NaCl and chlorine? 2 moles of NaCl per 1 mole of chlorine. So how many moles of chlorine NaCl should form theoretically? 0.4 moles. I know this is a stupid problem. I don't like this. So this is the theoretical yield, okay? And actual yield is also the same. So what do you think when you calculate the percent yield? 100%, which does not happen. As I said, you will see that 99.9% of the time there is no 100% reaction. If you get anywhere near 85, 90, we would say, wow, wonderful, good yield. That's what usually we would say. So the percent yield is actual over theoretical multiplied by 100. So your actual, which is given in the problem, is 0.40 divided by, you just calculated the theoretical yield, which is also 0.40 multiplied by 100, means 100% yield. That is what you will get in this problem. Oh, I wrote just above that. Okay. Let's look at another problem. Same reaction. Again, 0.450 moles of chlorine reacts with excess sodium. So chlorine is the limiting reactant. And 0.385 moles of NaCl are produced. What is the percent yield for the reaction? So this again is the actual yield. So we want to calculate the theoretical first. Theoretical yield. Let's calculate. How much chlorine we have? 0.450 moles of chlorine, which is the limiting reactant. So how much sodium chloride can form? What do we do? Multiply by the mole ratio. So 2 moles of NaCl per 1 mole of chlorine. Okay. How much we need? Or what is the theoretical yield? 0.9 moles. Right? When you multiply this number by 2, you will get 0.9. So this is the theoretical yield and this is the actual yield. So what is the percent yield? Actual over theoretical multiplied by 100. Remember that equation. So actually is 0.385 and theoretical we just calculated is 0.9 multiplied by 100. Oh, I'm speaking through my nose. What is the yield? I couldn't hear. 42.7. So again guys, the theoretical yield is calculated from the limiting reactant. Okay. So the amount of Liebig reactant, multiply that by the mole ratio of the product and the Liebig reactant. So you will get the theoretical yield. Then percent yield is actual over theoretical multiplied by 100. Okay, that is not exactly on the top. Okay, one more problem. You go ahead and do it by the time I come back. Oh goodness. Okay, so what is the actual yield? It's clear from the problem. What is it? 7.44. What is the theoretical yield? 8.95. Therefore, percent yield. So 7.44 divided by 8.95 multiplied by 100. What do we get? 83.113. Okay, that was a good reaction. She did well. Okay, yep, 83.1. Good. So, percent yield is okay? What? You can play with the clicker? Huh. Okay. Very easy question. Read carefully and just choose the correct answer. I'm putting pressure on you. I want 100% right answers. Did we have everyone today? Let's see, 22. Including Cody and Lewis, 22?
No, I already.
You counted 23?
That's because it's
Lewis is supposed to be here. Everyone else is in here, right? Did everyone answer? And everyone has the clickers? Okay, I know that he answered and then he left out. So, oh, 23 right there. Okay, what is the answer? A, D. What? What is the correct answer, guys? Okay. After a long time, I'm seeing 100%. So we are on to the last part of this chapter, energy changes. So when we know that when we burn Bunsen burner in the lab, it's a picture of that. We already learned that from last chapter, combustion reactions. We burn methane gas with oxygen and it gets converted into carbon dioxide and water, but this reaction produces a lot of heat, and that's the heat we use for whatever purpose we are using it, right? To boil water in the lab or at home if you are cooking food or whatever you are doing with the stove. So when you burn methane gas, it produces a lot of heat, and the heat is released to the surroundings, and we use that for different purposes. All chemical and physical changes are accompanied by some kind of energy changes. Okay, either visible or visible in the sense which you can feel it, or some of the energy changes you may not even notice, but there are some kind of energy changes associated with all chemical and physical changes. Now, the law of conservation of energy, or this is the first law of thermodynamics, it says that when energy is related from the atoms of a chemical reaction, it is transferred to the surroundings, and the energy released by the reaction is equal to the amount energy absorbed by the surroundings. This is where the calorimetry, the Tuesday guys have done that lab long time ago. Wednesday guys have done it yesterday. So the calorimetry principle also, the heat lost by something and heat gained by something else, they are exactly the same if you keep everything else insulated, right? Or in other words, energy is nor created nor destroyed. That is the law of conservation of energy, just like law of conservation of mass. However, energy can be converted from one form to another. That's what we do. That is what we use energy for, all the purposes. We are converting one form of energy to another form which we want. Say for example, what happens in an internal combustion engine. We are burning octane with air, and carbon dioxide and water are the byproduct. If it's a complete burn, but of course it's not a complete reaction. We have no engines designed so far which would do the complete burn or 100% reaction, and it produces a lot of heat. So much heat is lost out of the car, just like that, and some heat is converted to the work to turn the wheels, or in other words, run your car. If you really calculate the average, I mean it's not just the highly energy efficient car, just the average efficiency, only 32% of the heat energy produced in an internal combustion engine is used for driving our car. Rest is all lost to the surroundings. Well, in the winter months probably we use some heat for warming ourselves, right? But otherwise all the heat is lost to the surroundings. Now, when we say, so as it says, no conversion is totally efficient. When we convert one form of energy to another form, the maximum you get is like that mechanical and electrical conversion, like 98. That is very rare. No conversion is totally efficient. Some amount of energy is always lost to the surroundings in the form of heat. And when we say efficiency, it's the percentage of energy that ends up in the form we want. That's what we call efficiency. So here is this picture. What it shows is, let's say if you are starting with coal, burning coal, and 88% of the heat energy produced, we will use that. I mean, we can, if you burn coal, almost 88% we can save it to boil water, to make steam, which we can use it for turning the turbines, and that is this only 46% is being used for turning the turbines. That is, we are converting the heat energy to mechanical energy. Yeah.
46% of AT.
Yes. So first you started with here, 88% is transferred for this, and then whatever you receive here, 46% is converted for mechanical energy, turning turbines. That is what the mechanical part is. Now this is a good conversion. The turbines do a good job. 98% of whatever energy they receive, they convert to electrical energy. And when we use a light bulb, this is a regular old incandescent light bulb, not those energy efficient ones. When we use that light bulb, whatever electrical energy you receive, you are converting only 4% for the light. Why do we use a light bulb? For light, right? Only 4% is converted into light energy. Rest of the energy is just lost as heat. That is why those old incandescent bulbs, if you touch after it's been on for some time, you will burn your fingers because it gets so hot. The glasses get so hot. More than light energy we are actually producing, we are using it as a heater. We are wasting heat. So if you look at the overall efficiency, that is starting with coal to the light, overall you are using only 1.6% of the energy you created. Rest is all lost in the translation. The translation, I was just using the wrong word, just the movie name, Lost in Translation. Just lost in, all these steps you have been doing. It's not very efficient. But the newer bulbs, the CFL bulbs, average, again different types of bulbs have different rates, but on an average they convert almost 17 to 20% of energy. That is why we call it energy efficient. Of course, when comparing to 1.6, 17 or 20 is 10 times efficient, right? Which is good. Yes, Bill.
I know this is a little off subject, but what would be more efficient, the coal, water turbines from like a dam, or nuclear?
Well, nuclear power would be the most efficient. But then that has the most risk factors also. Yes. So turbines which are safe, but then the efficiency is so less. That is what the given process. Where is my, okay, right there. Now, as I said, most chemical reactions, all chemical reactions accompany some kind of energy change. Mostly we can convert or we can put them into two different categories. One category where the reaction is releasing heat when it happens. Those type of reactions are called exothermic. Well, the word exo stands for out and thermic stands for heat, right? Thermo means we know it's the word for heat. So exothermic means heat out. That is how it translates. So exothermic reactions, when you when the reaction happens, it releases heat. Those reactions are called exothermic reactions. Whereas some reactions, in order for the reaction to occur, it needs some heat, or it absorbs heat from the surroundings when the reaction is happening. So those type of reactions are called endothermic reactions. Again, endo is the word, endo means in. So heat in, or you need heat for that reaction to occur. So it would absorb the energy from the surroundings. Some of the reactions, even energy from the surroundings is not sufficient. That is when you need to actually heat it. You need to provide some heat. So these are the two major categories of reactions, exothermic and endothermic. Now, a regular day-to-day use of these two reactions. When we use hot packs and cold packs, what happens? Most of the hot packs, it has a chemical called magnesium sulfate and then water, just water, stored in two different pouches or two different containers, or magnesium sulfate and water is separated by a very thin liner. Now, if you remember the directions of most of the hot packs or cold packs, they say before you use, you crush it, right? Or knead the pack. What you are doing is, you are just by crushing or by kneading, you are breaking that barrier between the magnesium sulfate and water. When magnesium sulfate and water comes in contact, magnesium sulfate will dissolve in water, and that is an exothermic process, or that reaction will release heat. So let's say my arm here, it's paining and I want to put hot pack in there. So when I knead the pack, put on my hand, that reaction happens, it releases heat, and where the heat goes? It goes to the atmosphere, or it goes to the surroundings, right? So if it is on my hand here, then I feel the heat. That is when I say, okay, it's getting warm. Now cold pack works the opposite way. Cold packs have different chemical, which is called ammonium nitrate and water. Ammonium nitrate, when it dissolves in water, that is an endothermic process, or it needs some heat. So let's say now I want to use the cold pack. So again I need the pack, so I break the seal between ammonium nitrate and water. So now ammonium nitrate is dissolving in water, and that process needs some heat. So I keep it on my hand again. I feel my hand getting cold. Why? The pack is absorbing heat from my body to do the reaction. Because that process, that dissolving ammonium nitrate in water, it needs heat. It's an endothermic process. So if it takes the heat away from my body, of course I feel cold, right? When do you feel cold? When heat is lost from your body. So wherever you are keeping the pack, the heat from that part of the body is being absorbed by that pack, so you feel cold. That's what you want. Cold pack means you want to feel cold. So that is how cold packs and hot packs work. It's an exothermic and endothermic reaction going in that pouches. Yes. No, ice is just, again, if you think in that way, ice is cold, and if you are keeping it on your hand, ice is taking energy from your body and melting. For ice to melt to water, it needs some energy, right? If you don't do anything, if you keep it outside, it will just absorb the energy from the atmosphere and melt, but that will be very slow. Your body heat is higher than the room temperature. So if you put the ice on your body, you will see that you feel cold because ice is taking the energy from your... It is an endothermic process, yes. Ice melting to water is endothermic, it needs energy. So if you put the reactions into a graphical way, that is, let's say we have, this is the energy graph. So this is low, this is high. As we go up, yes, Cody.
Just to clarify on what you last said, now water is turning to ice. Is that exothermic?
That water turning to ice. Well,
Freezing, is it getting really?
freezing is removing energy, right? So you can call it as exothermic. Yes, because your heat you are taking away from water. That is when the water becomes ice. So if you look at this graph, this is energy graph where this is the low part, this is the high part. Now all exothermic reactions, so far what we discussed, we can say that the reactants are in a higher energy level, and when the reaction occur, the products which are forming, they are in a lower energy level. So there is a gap between the reactants and products in terms of energy, right? So what happens to that energy? That is what is lost to the atmosphere, or the energy which comes out of the reaction. Remember, exothermic, energy out. So reactants have higher energy, products have lesser energy, so the difference should come out. Now the opposite is true for endothermic, that is reactants have low energy, the products have higher energy. So how would this reaction occur if you don't supply that gap? It cannot happen by itself. You need to supply that gap of energy, then only the product can form. So either you give heat or the reaction would absorb heat if possible from the atmosphere, like from your body or from the air if it is possible. As I said, some of the reaction, this gap is too big, it cannot just use the energy from the air or from your body. Such reactions you may have to take it in a test tube and you may have to heat it. Then only you can supplement that gap. So exothermic and endothermic, you can think of this way also. Now we are going to look into the quantities of heat. So heat is again the energy that is transferred between two objects because of a difference in their temperature. In our day-to-day life, we kind of use temperature and heat as the same thing, right? But thermodynamically, those are two different things. Heat is not the same as temperature. Temperature is just a measure of how hot or how cold a substance is. But heat is a different quantity. There are no devices developed which can measure the heat. Heat is a quantity which you have to calculate. And in chemistry, quantities of heat or energy are usually expressed with the unit of joules. Joules is the unit of energy, or calories. Note that this calorie is not exactly the same as the nutritional calorie. The nutritional calorie is a kilocalorie, or 1000 calories becomes 1 calorie, and we differentiate that by the nutritional calorie is written with a capital letter C, calorie or cal, and the energy unit calorie is a small letter C, cal. And how they are related? 1 cal or the 1 nutritional calorie is 1000 energy calories, or 1 kilocalories. Now the conversion between calories and joules is 1 calorie is 4.184 joules. That is the conversion. So we have seen this word before, specific heat, when we did the calorimetry lab. So specific heat is defined as the amount of heat required to increase the temperature of 1 gram of a substance by 1 degree Celsius. That is the definition of specific heat. And as I said in the lab, specific heat for a particular substance is a constant for that substance. Every substance has its own specific heat. That is what it says, the specific heat depends upon the identity of that substance. Everything has its own specific heat. And the units of specific heat are joules per gram degree Celsius. And for specific heat of water, which is a constant, 4.184 joules per gram degree Celsius, and we have some of the other substances and the specific heat, some of the chemicals and some of the stuff which we see in our day-to-day life. Left side is mostly chemicals, specific heat given in joules per gram degree Celsius or calorie per gram degree Celsius. Right side is mostly the stuff we see. Is there anything interesting in there? Water has good specific heat, and then strawberries, wow. Wax, cheese, Anyway, so again, specific heat is the amount of heat required to raise the temperature of that 1 gram of substance by 1 degree Celsius. That is the specific heat. Don't worry, this is just for, kind of a comparison. Some chemicals and some substances, just the specific heat. Now comes to that, the equation you have seen before in the lab. Remember, heat is expressed using the letter Q, and it is calculated using 3 quantities: mass of the substance, specific heat of the substance, and the temperature change. So we can express that equation as Q is equal to mc delta T. I think in the lab, instead of C, they were writing SPHT, specific heat, in your lab notebook. But usually C represents specific heat, capital letter C. So this equation, remember this equation, there will be a question in your exam using this equation. Okay? Q is equal to mc delta T. Q stands for the heat, M stands for the mass, C for specific heat, delta T represents the temperature change. Now how do we calculate delta T? Temperature change is usually taken as T final minus T initial, or the final temperature minus initial temperature. That is how you usually take delta T. Okay, so let us just calculate. Let's do a couple of activities using this equation. So how much heat must be added to 15 grams of water to increase its temperature from 25 to 75 degrees Celsius? So what are we looking for? What are we calculating? We are calculating Q because it's asking how much heat. So we are looking for Q, right? And this is the equation mc delta T. Do we have all the data we need? We have mass of the water. We have initial and final temperature. So you can calculate delta T. And we need specific heat of water, right? That is a constant. In your exam, you don't have to by heart any specific heats. If whatever the question is, I will give you that particular substance specific heat. Okay? You will have the information given to you. So, just straight away putting the okay, so what is delta T? First let us look into that. What is our delta T? T final minus T initial. Read carefully. Which is the final temperature? Which is the initial temperature? So it says increase the temperature from 25 to 75. So initial is 25 to 75 means final is 75. So what is delta T? 75 minus 25. So delta T is 50 degrees Celsius. Now I'll give you the specific heat. Specific heat of water is 4.184 joules per gram degree Celsius. So let us substitute the numbers into Q. So Q is mass is 15 grams multiplied by 4.184 joules per gram degree Celsius multiplied by 50 degrees Celsius. So again degrees Celsius will go away, gram will go away. So you get the Q in units of joules. We already learned that the unit of Q is joules. So how much heat you should give? It's just direct multiplication, right? Three numbers multiplying. How much heat, guys? 3,138 joules. Okay. Now, here the question is, what is the heat change when 15 grams of water cools from 75 to 25? Well, you can answer this logically also, but if you have to calculate, what would you do? What is the delta T here? What is the initial and final temperature? The water cools from 75. That means initially the temperature is 75 and final temperature is 25. Delta T is calculated as final minus initial. So 25, which is the final temperature, minus initial temperature, which is 75. So what is delta T? Negative 50. So when you calculate Q, anything changes? So when you calculate Q, what you should be getting? Negative 3138 joules. Right? Since the mass did not change and since it's the water, specific heat is a constant, so only the sign changes. So that again tells you, whatever the amount of heat you given to increase the temperature from 25 to 75, that must be exactly the same amount of heat you need to remove for cooling the water from 75 to 25. Okay? Now, the sign of Q is important. Sign of Q tells us couple of things. Oh, here the calculation again. Well, I guess they have rounded off, so 3140, doesn't matter. So, the sign of Q is important because the sign of Q tells us couple of things. And what is the meaning of Q? Again, remember the principle, law of conservation of energy, that is, whatever the energy cannot be destroyed or created. So, whatever heat lost by a substance, it has to be absorbed by the surroundings, and whatever the heat absorbed by the surroundings has to be equal to the heat released by the system, right? Or in other words, when you add the Q of the system and Q of the surroundings, it should be 0. What does this mean mathematically? Q system plus Q surroundings is 0. What is the meaning of this mathematically? Q of the system, oops, no, how can both equal to 0? Q of the system will be equal to negative Q of surroundings, right? Because we said that the heat lost by the system, it is absorbed by the surroundings, exactly the same amount of heat, right? But it's just that they are opposite in signs. Their numbers are exactly the same, but their sign is opposite. So Q of the system has to be the same number of Q of the surroundings, but with a negative sign. And when you add those two, you should get 0. If both are exactly the same numbers, one is positive and one is negative, then when you add them, you should get 0, right? Let's say, for example, Q of the system is 10, then Q of the surrounding is negative 10. When you add them, what do you get? 0. That's what mathematically this means. Q of the surroundings and Q of the system, they have the same numerical value, but their Sign is opposite. Now, little more in detail, let's say the system means whatever reaction, whatever you are looking into, and surrounding could be the outside. So, if the system is releasing heat, what do we call those type of reactions? Something releasing heat? Exothermic, heat out, right? So, then the system is releasing heat, that is an exothermic reaction. And when the system is releasing heat, when you calculate Q, Q will be always negative. Like water cooling from 75 to 25. Water is the system. Okay? It is cooling from 75 to 25. Heat is lost. Heat is lost to the atmosphere. When you calculated Q, what was the sign of Q? It was negative, right? So, or in other words, Q will be less than 0. Less than 0 means it's negative. Anything less than 0 is negative, right? So, when in an exothermic reaction, heat is released, and when you calculate Q, that will be always less than 0. So, in an endothermic reaction, the system needs heat. Water is, we are heating water. Water is going from 25 to 75. So we are supplying heat to the system. It is an endothermic reaction because water is absorbing heat, right? So that is an endothermic reaction, heat absorbed, and when you calculated Q, what was the sign? Was it positive or negative? It was positive. So basically that sign comes from the delta T sign. Delta T is T final minus T initial. So if something is cooling, your T final is small, T initial is large, right? Because cooling means from a hot temperature to colder temperature, or from a higher temperature to a lower temperature. So when you take the final minus initial, your delta T is always going to be negative, and cooling is always exothermic because you are releasing heat when something is cooling. Make sense? When something is cooling, heat is released. So it is an exothermic reaction. Whereas when you heat something, you are providing heat. Or delta T will be positive. So when you calculate the Q, that also will be a positive quantity or greater than 0. Endothermic, Q will be positive. Endothermic is the process of heating. That is, something is cool and you are raising the temperature, or you are providing heat. So let's do some more calculations today, and we will stop after we do the specific heat calculations. So here is the question. The specific heat of aluminum is 0.895 joules per gram degree Celsius. If 156 gram of aluminum at 75 degrees Celsius is cooled to 25 degrees Celsius, how much heat is transferred? What is the sign of Q and what is its significance? Means whether it is an endothermic or exothermic reaction, because sign of Q will tell you that. Okay, so can we calculate the Q? Do we have all the data we need? Okay, so go ahead and calculate Q for the metal. So what is the mass? Remember the equation. Q is equal to mc delta T. Remember that equation, please. As I said, there will be a question. You need to remember that equation for this. So what is the mass? 156 grams multiplied by, we need specific heat, which is C, 0.895 joules per gram degree Celsius, multiplied by, we need delta T. Delta T is T final minus T initial. So what is the final temperature? What is the initial temperature? aluminum is at 75 degrees Celsius. So that is the initial temperature. It is cooled to 25, means after cooling this is the temperature. So this is the final temperature. So 25.5. This is important, guys. Read the line carefully and write it down. Otherwise you will end up with doing the wrong thing, that is your delta T sign will be the opposite. If you just look at 75 to 25, you will just use the positive value, but is that the sign of delta T? No, delta T is T final minus T initial. So this will be negative 49.5, right? So now you put that number, negative 49.5 degrees Celsius. So what is the Q? Negative 66911. What are the units? Joules. Note that the units will cancel beautifully. The gram and gram will go away here. Degree Celsius and degree Celsius go away here. So you are end up with the units of joules for Q. So, okay, so we calculated the Q. So it's asking what is the sign of Q? Of course, it is negative. And what is the significance? Q is negative means what? What reaction is this? It is an exothermic reaction. Q negative means the temperature is released or temperature is removed from the metal to the surroundings. So you can say from the negative side of Q, you can conclude that this is exothermic. So yeah, well, they've expressed that into scientific notation 6.9 1 into 10 to the power 3 joules. So the side of Q is negative, that means the process is exothermic, or it releases that much heat into the surroundings. Okay, how about I'll stop right here today. We will do calorimetry and finish the chapter in next class. And then remember the exam is Thursday. Yes.
We're all going to study hard.
Yes.